Yeah, and our next guest today is Dr. Tom Hull. He is an associate professor of mathematics at Western New England University, and he is considered a leading expert on origami mathematics. He received his PhD in graph theory from the University of Rhode Island, and he has written origami instruction books and research papers. His most popular origami creations are the fizz unit and the 5 intersecting tetrahedra model, which is voted by the British Origami Society as one of the top 10 origami models of all time. His talk today will be on origami and math, paper, polymers, and robots. So without further ado, please welcome Dr. Tom Hull.
Hi, thanks, Catherine, and thanks for inviting me to this this event. This is kind of amazing what you're doing here. It's cool. So let me share my screen and get this started. So yes, I'm talking about origami and math, which is about, well, a lot of things. But before I start, I should point out that it is, I think, illegal to give a talk on origami without having people actually fold something. So we are going to do a little bit of that. It'll come up in a few minutes. If you have, all you need is a piece of paper and a pen, and it doesn't matter what shape piece of paper. I just have an 8.5 by 11. So if you can scrounge a small piece of paper, you'll be good to go. Having a pen is nice too. But anyway, yeah. So I just want to give an overview of something that's kind of like a passion in my life. I've been doing origami since I was 8 years old. I'm also a mathematician, and somewhere around college, grad school, they started coming together, and that was really kind of awesome for me. I got to take a hobby and turn it into a career in a sense, or merge it into my career as training to be a mathematician and a math professor. So I want to give you an overview of like what that's about. This animation you see, which is just an animated GIF, that's kind of like, well, you'll see. I'll talk more about that later. But just the fact that I can make this animated GIF that is simulating something called rigid origami is means there's like a lot of math to unpack just from something like that. So but first of all, what is origami? Most of you probably know, or hopefully you've folded something, or you might wouldn't be here. But yeah, paper folding. You're folding paper. It's a Japanese word. Ori means fold. Gami means paper, kind of. And normally, you fold things like cranes. That's what we see here, an origami crane. And if you unfold it, you get something called the crease pattern. And that is like a blueprint of the model. And that's where a lot of the math exists inside an origami model. The kind of basic question is, like, how do you go back and forth between folded object and crease pattern? There's clearly a connection. In fact, I remember being at like 12 or 10 years old, folding models because they were fun, because I thought it was cool, and I really liked doing it. But somewhere around then, I unfolded. It might have even been this model, this classic crane model. I unfolded it and looked at the crease pattern and immediately thought, oh, look, it's math. There's certain angles, there's certain things going on here. And so that's kind of like maybe what started me thinking about the connection between origami and math. But I was 10, I didn't know what I was doing. But one thing that ends up being really important that we're going to talk about later is whenever you fold something, especially if you fold something flat like this crane, the creases come in two types. You have a mountain crease or a valley crease. And that tells you which direction they're going in. If you're looking at the paper from one side, some of the creases are coming up at you, making a mountain. Others are going away from you, making a valley. So more on that later, because there's some fun math there. But just to kind of give an overview, you got classic traditional origami. Some of you may have folded these models before. These origami pieces, as origami folds people have been doing them for hundreds of years. They go back to ancient Japan, like at least the 1600s or 1700s. No one really knows for sure, but classic Japanese crane, classic Japanese frog. Yeah, that's like ancient origami. More modern origami looks kind of crazy, but there's a lot of it, and you can find a lot of it on YouTube or by searching the internet for complex origami models. This is one of my favorite. It's made by a guy named Mayakaws, who is a Japanese physicist and an origami artist. It's his Demon. It's on the cover of this book called Viva Origami that was published in the 1980s. And this is the crease pattern for it. And it's way more complicated than the crease pattern I showed you before. But it's still, this is like one square piece of paper, no cuts, and you get all this detail. 5 fingers on each hand, a tail, legs, eyes, tongue. It's all here. It's all here somewhere in the paper. And studying complex origami is really kind of amazing. Here's another example of more modern origami. This is Satoshi Kamiya's wasp. And there are a lot of origami wasps out there, but this has got to be the most complicated one I've ever seen. Unlike Mayakaws Demon, where if you can find a copy of this book, or there's some other books that have this in it, if you Google Mayakaws Demon, you might find instructions online. There are instructions. You can fold this step by step, okay? This one, no, you can't. I mean, well, at least no one's tried writing down step-by-step instructions. If you want to fold this wasp, you got to, this is the instruction right here. You find this crease pattern online, and then you try to fold it. It's really, really, really hard. But the amount of detail is amazing. And you can find a lot of origami models that are kind of like this. This is a model called Attack of the Kraken by Brian Chen. I really like this. This is, again, one piece of paper. And you got the squid, you got this boat with sails and stuff, all one piece of paper. Here's the crease pattern. He decided to give it a Pirates of the Caribbean kind of look, which is kind of fun. But, you know, this big, I don't know, like rhombus-like region, that's the sails, that makes the sails of the boat. Whereas, I don't know if you can see where the Kraken goes, but, well, the squid body is right over here. There, it says squid there, and there's the eye of the squid. And so it's like, it's amazing that you can do this. You know, the fact that you can like develop origami models that are this complicated is really kind of amazing. And it's no, you know, comparing like ancient origami to this more modern origami, the origami developing in complexity does go in parallel with our greater and greater understanding of the mathematics behind origami. That's not a coincidence. Okay. So to give you a feel for how understanding some of the math can help you with crease patterns like this, or crease patterns like Satoshi Kamiya's wasp, I'd like us to do an activity. Okay, so this is where the paper comes in. So if you have a piece of paper and you have a pen, the only reason why I suggest a pen is to draw a dot in the middle of your paper. So I'm going to do that. I have a piece of paper. I'm going to draw a dot on it. So I would like you to do that too, if you can. Okay, and here we're all going to discover an origami theorem together and then take a look at the proof. Okay. So take a piece of paper, draw a dot in the center, and then what I want you to do is make a crease going through your dot. Okay, so you want to look at your dot there and make a mountain crease. Okay, that just goes through your dot, and it could be anywhere. So make it at any angle, but you know, a straight crease going all the way through. You want to be able to see your dot though, so make it go through your dot. Okay, and then I want you to do that again. Leave it folded. Okay, leave your piece of paper folded, but then make another fold through your dot. And it could be a mountain or a valley, doesn't really matter. But you know, make it at some angle. I'm going to do mine like this, but yours might look different. You might make it look like that, but you know, you get to pick how this works. Okay, and you want to do that a couple of times. Okay, like you could stop here if you're satisfied with what you just did. You can stop there, or you can flip your paper over and do it again. Make another crease that has to always go through your dot though. Okay, and so do this a couple of times. You get to decide when you want to stop. Okay, so everyone's will look different. What we're doing is gathering data to make a conjecture that we're then going to prove. This is math. This is how we do math, right? Okay, so I'm going to stop here. You can do some more if you want. You want to make your creases sharp. Okay, so either use your fingernails or put it on the table and like rub your fingernails to make them sharp. Okay, because then what I want you to do is unfold this. Unfold your piece of paper and then look at your dot. And what I want you to do is, coming out of the dot, you will have mountains and valleys. And what I'd like you to do, and I'm going to actually stop sharing my screen because I want to make sure I turn on the chat, although I'm going to share a different screen actually, so that way I can keep track. I want people to tell me in the chat window how many mountain creases and how many valley creases you have coming out of your dot. Okay, so I'm going to try an experiment here. I'm going to share this screen so I can keep track of the numbers you share. And then I have to open the chat window. So again, you're coming out of the dot. Like I have 6 crease lines coming out of my dot, and some of them are mountains, some of them are valleys. If people could type in the chat window how many mountains you see, how many valleys you see, I will record them on here. And yeah. Oh, wait, I got to go down. I haven't. So no one's told me what they have yet. Or you can unmute your microphone and just tell me verbally if you're feeling brave. How how many valleys, how many mountains. You can't really get this wrong unless you don't count properly. But okay, so someone says, oh, wait a minute. Someone says 4 mountains, 3 valleys. And someone else says 4 mountains, 4 valleys. Be careful. You want to, and someone says 7, 5. You're counting each crease coming out as different. So I have 6 creases coming out. So my total should be 6. Okay. So I don't think you can get 4 and 3. So you might want to recount 2 and 6. Some of these numbers don't make much sense to me. So I wonder if you're counting correctly. But someone got 7 and 5. That makes sense to me. 4 mountains, 2 valleys. Okay. Yeah, so you do have to count. So let's see, what do I have? Oh, I have 4 and 2 as well. I have, let's see, what do I have here? Here's a mountain, there's a mountain. I have 2 mountains there, 2 mountains there, and then 2 valleys. So the total is 6. 3 mountains, 5 valleys. Cool. Yeah. The thing is that there's something going on here. So, and then someone else got 7 and 5. I already have that down. Of course, if you turn your paper over, you could get all your numbers switched, right? 2 mountains, 8 valleys. I don't believe that. See, whoever did that might want to count again. This is one thing, another easy thing to make mistakes is if your creases weren't sharp, it's easy to forget. Or if you made too many, 5 and 3. Well, that's kind of like 3 and 5 if you turned it over, but still, that's okay. So I'm curating the data slightly because I know what's supposed to work. But does anyone see the pattern in these numbers? I know there's at least a few people listening who already know the answer to this, but there is a pattern here. Does can any of you see what it is? One thing that's interesting, yeah? I thought I heard someone.
They add up to an even number.
They add up to an even number. That is absolutely true. It's not what I was looking for, but it's absolutely true. You can prove that as long as you fold something like this flat, you know, that every vertex in your crease pattern, if you fold it flat, has to have an even number of creases coming out of it. That's definitely an origami theorem.
One is 2 more than the other.
Yeah, the difference of all these always seems to be 2. In fact, let me do another one quickly that it looks like all of you, none of you wanted to stop after just 2 folds, but even if you just did 2 folds, so you only have 4 creases, like here I have what? Mountain, mountain, valley, mountain. So another possibility, you can have 3 mountains and 1 valley. That's like one of the most simple things you can do. You know, but yeah, that is basically it. The difference between mountains and valleys is always 2 if you're folding something flat, doing what's called flat origami. Okay, so I'm going to go back to my slides because that origami theorem actually has a name, and it's and I'd like us to take a look at the proof because hey, that's what math is doing. Okay, so yeah, so this result is called Mayakaws Theorem. It's named after the same person who made that demon, Zheng Mayakawa. And it basically says this: if you let V be a vertex in a flat origami crease pattern, and M and V be the number of mountains and valleys, then if you subtract them, you always get either plus or minus 2. And whether it's plus or minus depends on what side of the paper you're looking at, right? That's what's happening there. Okay, so there's a lot of ways to prove this, but I like doing a proof like this because this is the kind of thing where if you were to just try to sit down and prove it, like where do you start? This is very much applied math in a sense. Like we're taking something physical that we observed and a conjecture that we made about something physically folding a piece of paper, and now we're trying to prove that that's always true, but we don't have any machinery to start with, except we do. There's lots of math you can apply to these things because there's a little bit of geometry going on here. We're folding paper, but there's also some combinatorics. It's interesting. So here's one way you can approach this proof. And that is to do something you're not allowed to do in origami, and that is use scissors and cut off your vertex. So imagine, so here I have a little cartoon of a crease pattern with only 4 creases, but okay. And imagine all we know is that it folds flat. So we fold it flat, and then I imagine cutting the vertex off. Do that because I want to look at the cross section, which is actually a polygon if you think about it, but it's a flat polygon. So I can actually demonstrate. Let me demonstrate that with my piece of paper. Here's the one I fold. I'm going to cut off the corner there, and then what I have here is a polygon. If I open up the paper a little bit, you can see it. And I don't mean that this polygon, I want to leave it folded. Okay, so it's folded, and it's like some zigzag polygon. If I open up the paper a little bit, I'll actually have angles, but it's actually a flat polygon. But it's really the cross section. That's what I'm looking at. So here's what I want to do with that cross section. I want to do something that's called a proof by monorail, okay, which is a technique we use in origami for more than one theorem. So this is actually a thing. So this little picture I have here, that is supposed to be a monorail traveling along the cross section. That is not a purple finger with teal fingernail polish. It's supposed to be a monorail, and monorails travel along these tracks. They hit corners and turn, and they come back to where they started. So the question I have is, if we look at this cross section, so I'm looking at the cross section from above, and I'm imagining, you know, like this, and I'm imagining the monorail going back and forth along this flat polygon. Now, imagine some of these creases are mountains and others are valleys. So, so let's see if if every time I hit a mountain crease, I'm going to rotate by 180 degrees, okay? Because this is a flat polygon. And every time so if this is a mountain, I'm rotating by 180, and then I hit this mountain 180. But then this one in the middle, that's a valley crease. I'm going to rotate by negative 180 degrees, and then 180 degrees again. Then I'll come back to where I started, right? So every time I hit a mountain, I rotate by 180. Every time I hit a valley, I rotate the opposite direction by negative 180. And what I want to do is like, well, I come back to where I started. So the total rotation should be 360 degrees, because I'm just going around a circle and coming back. When I come back to where I started, the monorail will be in the same orientation as where it started. So this total rotation, 180m minus 180v, should be 360. And you know, just you divide by things, and there you go. M minus v is 2. And that was assuming that I had more mountains than valleys. If I flipped the paper over, I would have gotten -2. You know, so or v minus m equals 2. Yeah. So that's an origami theorem. And it's things like that that allow people to study origami design or do other things too. Okay, so so next I want to kind of go through quickly like various other types of math that are involved in origami. This Mayakaws theorem that we just saw, this is actually a combinatorial result. It's about counting mountains and valleys. It uses geometry in the proof a little bit, but it's really about counting things. Still, there is a lot of geometry in origami. You can, when you fold paper, you can think of it as like doing a geometric construction. And I could do a whole talk on that. You can actually show that with origami, you can trisect angles. You can actually do more than you can with straight edge and compass. That's a lot of fun. But it's like straight origami geometry. But there's other things too. And this thing, this is called Kawasaki's theorem, has to do with, is really important for origami design. And that's like, if you fold, again, if you have a flat folded vertex or a crease pattern that folds flat, and you look around any vertex and you look at the angles between the creases, this is a very much a geometric result. Then if you add up the opposite angles or every other angle, so here alpha 1 plus alpha 3, that's got to equal 180. Or alpha 2 plus alpha 4 has to be minus 180. Another way that people phrase that is if you take the alternating sum of the angles, alpha 1 minus alpha 2 minus plus alpha 3 minus alpha 4, and so on. Doesn't matter how many there are, the alternating sum will always be 0. That's actually equivalent to writing it as 180 degrees. But that's nice because this is actually an if and only if theorem. If this angle condition is true, then your vertex will fold flat. There's a way to go back and forth. So this is actually a very useful theorem about the geometry of flat origami crease patterns. Yeah. And another thing, this kind of ties in a little bit to what Corinne's talk was about. We can think of an origami crease pattern as a graph with vertices and edges. And one neat thing you can prove about this that has to do with what someone observed when we were doing our experiment is that if your crease pattern folds flat, every vertex will have an even number of creases coming out of it. Okay. And you can use that to prove that if you want to color the faces of your crease pattern, you can always do it with just 2 colors. There's a way to do that in graph theory, that if you have a graph and every vertex in its interior has even degree, has even number of edges coming out of it, then you can always 2 color it. But there's another way to prove this that's even more elementary. And that's that to imagine what would this look like? Like, remember, this is the crease pattern of that crane. What would this look like if I actually folded it up again? Well, I would love to spend time for you to think about it, but this is what happens. All of the white regions end up facing in one direction and the gray regions face in the other direction, which makes sense. Everywhere there's a crease, you're folding in half, you're folding the paper flat, so the white will point in one direction, the gray will point in the other. So you get this neat thing where if you end up with your crane, but if you flip it over, it turns into the other color, which is kind of fun. If you know how to fold something like this, I highly encourage you actually try doing this. Fold something flat, unfold it, color it like this, and then fold it again. It's fun. It's really fun. What else can you do? Here's something that was surprising to me when I first encountered this. You can model origami with matrices. And this does make sense because you use matrices or matrix transformations to do geometric transformations in space. And this goes beyond flat origami. So this is a picture of a three-dimensional thing. This is called a corner of a cube. It's just, you have these 5 crease lines, and this makes a 3D vertex that folds into a corner of a cube. And you can model what the paper is doing along each crease with a rotation matrix. And you want to think of this as just something that's telling you what is the paper doing if we were to rotate, say, by pi/2 radians or 90 degrees about, say, this crease line along the x-axis. Well, you would use this rotation matrix. I would put pi/2 into theta here. And that is something I could use to actually model it folding. The cool thing about that is that there's a nice theorem that says that as long as your paper doesn't tear or stretch, which is always the case with origami, then if you multiply all these rotation matrices together around a vertex, you should always get the identity matrix. And this is a way of combining linear algebra or matrix algebra with origami. What's great about this is that it is matrix products like this that allow us, that give us what we need to do animations like this. These are animations. I did them on Mathematica, and it's a computer simulating origami. There's no real actual folding happening here, but what these matrices allow me to do, and then there's this one, which no, I don't think I showed you that one before. What they allow me to do is figure out the folding angle relationships between all the creases. Okay, and that all comes from this one equation. All of these animations were done basically by exploiting this equation. And that's something that's actually been really interesting to engineers and physicists. But before I talk about that, I just have this slide of where I just try to make a list of different type areas of math that actually apply to origami. This is something that's been really exciting for me as a mathematician who loves to do origami. As I study more about the connections between math and origami, I'm continuously amazed at you give me an area of math, there's probably some way for me to use it to study origami, or vice versa. There's maybe some way for me to use origami to study that part of math. Everything from, like I said, geometry, matrix algebra, combinatorics, and graph theory. We've already seen examples of that, but there's others. Statistical mechanics, which is like kind of advanced, but something that physicists and chemists use a lot. Analysis, differential geometry, and topology. All of these things are things that have a really rich amount of connections between origami and these subject matters. So what I wanted to end with was a couple of examples. Here, I'll just start playing this, of people actually using origami. This has been a lot of fun for me because for the past 10, 12 years, engineers and physicists have been getting really interested in origami as a way to make applications. So what you're seeing here is some research from the Harvard Microbiotics Lab from 2009, so over 10 years ago now, where they made one crease pattern, and these little discs are kind of like magnets to help hold things together, but the crease lines are wires, and if they electrify them, then they can make this crease pattern fold into different things. So this is one crease pattern that they're able to fold into a boat here, or the thing that we saw first, I forget what it was, but yeah, what was the, it was a boat, and was the other one a hat? Yeah, anyway, it's not a, that this is like an airplane or something like that. What people want to do with this is that they're envisioning origami transformers. Like, could we create some kind of origami structure, much more complicated than this, that could fold into two different things, like a boat or a plane or yeah. So And people have done much more with this. So that was 2009. This video is from 2014. Again, the same group at Harvard. I should try to maybe speed this up if I can. It's not giving me any control, so maybe I can't. But this is people trying, the same group trying to make an origami walker. So this is something that is literally folding on its own, although it has these engines. But the engines don't come into play until later. What's happening here is that they programmed this thing, they created this thing, and now they're heating it up, and it's creating these folds. You can see it, and this is actually happening kind of slow. This is like 8 times the normal speed of time. And so they're heating this up, and that's making the creases all actuate at different rates at different times. And then eventually, once everything gets folded, the motors kick in, and then this thing can walk away. But it started, yeah, there it goes. It started flat. So that's kind of cute. So people are actually trying to use origami concepts to make robots, and you might wonder why, but there's a bunch of reasons. So here's another animation I can show you. This is something called the mirror map fold. This is one of the earliest examples of people trying to apply origami. This guy named Koryo Miura came up with this fold. I actually have one here to prove to you that this really does work. It takes a large piece of paper and it compacts it to something pretty compact, but it folds and unfolds very nicely. Like this animation is modeling it, you know. Miura, who invented this, wanted to use this as a way to put solar panels in outer space, because you want solar panels to be really big, right? And so, but you can't just send something big into outer space. You have to put it on top of a rocket or inside a capsule or something. And so if you have a way to fold up a large solar panel, put it into a capsule, send it into outer space, and then have a nice way to unfold it without the aid of human hands, then you could conceivably get a really big solar panel thing out there. So that's one way that origami is useful for deployment, you know, of things, maybe in outer space. But for robotics, it's interesting because, again, if you can create a robot from a 2-dimensional sheet that then can fold into a robot that you can use to do something, well, that's easy to manufacture. It's got a certain level of simplicity of construction. And there's some other things going on there too, but the last example I want to show you illustrates. So this is an application I had something to do with. I worked with these people at the University of Massachusetts, Kristen Santangelo and Ryan Hayward, and they came up with this way of folding these things called polymer gels. I'm going to try to go through this quickly, but the real, without getting into details, what they would do is sandwich two layers of stiff polystyrene around a layer of grow animal material. Grow animals swell when you get them wet. Okay, so the middle layer here, that will swell when it gets wet, whereas the blue layers won't. They remain stiff. And they can make these things really, really thin. This is like 1 nanometer thin. These things are really, really tiny. But what they do is they carve these trenches to control where the swelling happens. So wherever there's a trench here on this cross section, if the trench is on the top and it swells, it'll give you a mountain crease. If it's on the bottom and it swells, it'll give you a valley crease. And so they take the mountains and the valleys and they carve them into the top layer and into the mountains are on the top layer, the valleys are on the bottom layer. And then they can actually, by dunking these tiny things into water, make them fold. And the width of the trench that they make, that controls what folding angle you get, how much you want it to fold. So they had a lot of control over this. This was really promising. And when they developed this, they approached some origami people like me and a guy named Robert Lang to say, okay, tell us what we should use for proof of concept. So one thing they did was they made this, that they wanted to make an origami crane, but the problem is they need all the creases to happen at the same time. There is a challenge with this method of how do you make things fold sequentially? But they did this. They got this flapping bird. This is the normal piece of paper, but this is an electron microscope version of their tiny 100 nanometer model. To give you an idea of how small that is, you can see that here. This is this little red dot there, and that thing right next to it, that's a grain of rice. That's how small this is. Okay. In fact, to show you that there's a blow up, that is the crane there. So these things really work. Another thing they wanted to do is have this fold a mirror map fold or mirror ori, because that's what everyone does in physics. If they get something cool, they want to make a mirror ori out of it, just because it's kind of a classic model, but also it's a good challenge too. So here you can see the mirror ori folding and unfolding. This is like less than a millimeter wide. This thing is super tiny. And so again, we have to, video recording this is kind of tricky, but that's the nice thing about this is that, yeah, you get it wet, it'll fold up, and then if you dry it out, it'll unfold. So this is repeatable. One thing they asked me to do is come up with something really complicated. They wanted to really say, like, can we do something really complicated? So I gave them this thing, which is like an origami tessellation that makes this 3D thing. This was kind of interesting because I gave them this crease pattern and I gave them information about it, but it didn't work so well at first. And that's because the postdoc they had working on this didn't get the geometry quite right in terms of predicting what folding angles it needed. So I had to do some more work with them. So here it's like not quite folding like it should. But then by making the folding angles more accurate, by getting the geometry to work out a little bit more, they were able to do better. But this was after 15 minutes of swelling, and part of it folded well, other parts didn't. What they found kind of amazing is that just by waiting longer, so after 2 hours, most of it did actually fold up. There was still a little, something going on here, but with more time, they were actually able to get it to work. They did make a video of this unswelling, so they dried it out, and I guess I probably have to hit this, yeah. They let it dry out, and then it boom, unfolded, and then they got it wet again, and it actually worked a lot better the second time. I guess it learned what it was supposed to do. So again, this is an electron microscopy image of this thing, which is again less than 1 millimeter wide. This is interesting because these are soft polymer gels. They're water-based. You could inject these in a human body and it wouldn't care. There's nothing really nasty chemical about these kind of things. So one of the things they're envisioning of using this for is something called targeted drug delivery. Imagine you had, we're trying to fight a cancer tumor site, and you don't, rather than flooding your whole body with chemotherapy or radiation or something like that to try to fight it, imagine instead you could have a little origami ball that closes up around a really toxic cancer-fighting drug, inject that into the human body, and somehow program the creases so that if they reach, say, the pH level of a cancer tumor site, then it will unfold and release the drug in hopes of hitting the tumor site. That's one thing that biological engineers are trying to perfect for medicine. And origami could be a way to actually do that. Anyway, I hope that was interesting, and I'd love to answer questions. If you want to know more, please feel free to email me. There's my email address. And I guess I always have to mention that a lot of the research that I've done here, especially the stuff I've shown you, has been funded by the National Science Foundation. And one of the things they make you do is whenever you talk about it, you have to say, oh, the National Science Foundation. But yeah, there you go. Yay. Any questions or whatever?
Yes, I have a question.
Cool.
So how do you fabricate a lot of these different memory materials, like things that can actually memorize their shapes or memorize configurations? Because I know they're a lot more than just polymer based.
Yeah.
So how are they fabricated in a lab, and can you actually reproduce those fabrications? Because I'm really interested in that stuff.
That's a huge question. There are a number of, and this is where the engineers come in. I mean, these physicists that I worked with, some of them had, or one of them had engineering training as well. That's how they were able to come up with this idea. But there are a lot of engineers that are really interested in finding ideas, ways to fabricate things that will fold predictably, like you say. There's something called shape memory alloys that have been very popular.
Like nitinol?
Yeah, I don't know the chemical composition of a lot of them, but the idea is, yeah, that they take a piece of metal and like the simplest examples are just like tubes of metal or like a paper clip or something like that. But they treat certain parts of it so that when it heats up, it'll fold into a certain shape. And that would be one that's heat activated as opposed to say water or some other type of stimulus activated. But they can also do it with a flat sheet using, I think, the same techniques. The problem there is that is getting these things to work predictably when you have lots of creases coming together. The nice thing about this polymer gel technique is that it didn't seem to mind the complexity level at all. With enough time, it would swell into the right kind of thing. But with shape memory alloys, sometimes they fold into kind of the wrong thing. Like some of the vertices might pop in the wrong way and stuff. And so how do you control for that? And that requires another level of technological innovation. But yeah, shape memory alloys is one. I'm trying to think if there are others. there was another one where people were just trying to find ink that they could put on a piece of paper, so that again, if in humidity, as it got wet, the ink would contract, and then so you could literally paint your crease pattern on, and that would be another way to do it. But that's folding out of paper as opposed to metal or something more stiff or something like that. But there's tons of ways that people are trying to invent, ways to have things self-fold. The robot I showed you from the Harvard, or those 2 videos from the Harvard lab, those were 2 different techniques they had. One was using electricity along wires to cause a contraction to happen. The other one was heat activated joints that they had between these panels of, I think, like really thin board or something like that. Or maybe it was plastic, I'm not sure. Yeah, but so big question. Yeah. Oh, I see. I think I missed some other questions too. Someone asked, what was my favorite application of origami in scientific research? I don't really know yet. Well, actually, one thing that I thought was really cool, but it has not been fully made yet, is someone came up with an origami heart stent. So a little origami tube that can fold into an even tinier tube that you could thread into someone's arteries and have it then open up and unclog an artery. It's a great idea. I think there's some people that still want to try to make that work, but it has not yet gone to like no humans have them in their bodies yet. But that'd be kind of cool if you could do that. Yeah. As far as the fascinating things, I think the space applications are the most fascinating things I've seen, because NASA's really interested in this. They actually I've met researchers at NASA who do have expertise in origami, and they want there to be solar sails in outer space that unfold, and there's a lot of work being done on that. Nothing has actually been launched that's super origami. Well, so the mirror map fold does exist in some satellites, but NASA is still working on a lot of things and that stuff is really kind of cool. Anything else, or should we should probably move on, I think.
Okay, so if there are no other questions, I think we're just going to move on. Thank you so much for your time.
Yeah, sure.